So this is the second day in-person class at BIT on chapter 5. Yesterday we discussed the first part of chapter 5. We can quickly summarize it, which is dynamic soil properties. And we've seen some introduction field tests or geophysical tests with low and high strain field tests. We have seen also lab tests, resonant column test, traxial test, and today we'll start from section 5.3, which is cyclic shear test, and we'll try to complete 5.4, stress strain behavior of cyclically loaded soils. So unfortunately, yesterday it didn't record much, but we'll go back and do the recording at some point for whatever we missed. Section 5.3 laboratory tests. We have seen resonant column test, and then high strain part, which is a traxial, cyclic traxial test. So cyclic traxial, the test itself is axial. That's the main difference between traxial and cyclic shear. In this case, the direct output is elastic modulus because it's axial loading. The axial load, or the cyclic load we apply, it's helping us to get the hysteresis loop. And from the hysteresis loop directly, we get E, the elastic modulus. And indirectly, we get the G, which is the shear modulus by assuming undrained condition. But in the case of cyclic simple, or sometimes called cyclic direct shear test, the load we apply, you can see it here. This is a soil sample. And instead of applying a load like this axially, we are applying it laterally. So this is like a shape table. So the load is, this is a horizontal load cell. You see it laterally moving. So it's a shear load on the soil sample. So depending, and we do have so many recordings, displacement, strain, and we get output hysteresis loop. But in this case, the direct output, because it's shear strain and shear stress, the slope is now shear modulus. And the average shear modulus in the hysteresis loop, which is connecting the 2 points in the hysteresis loop, it's a second shear modulus. That's the main difference between cyclic simple shear test and traxial test. In case of traxial, it's normal stress and strain, so you get elastic modulus. So for soil, we're mainly focusing on the shear modulus representation. So the cyclic simple shear test is the best method to get the shear modulus compared to the traxial test. So if we summarize, in the cyclic simple shear test, a short cylindrical specimen restrained against lateral expansion by rigid platens. So this rigid platen is this one, this member. In some cases, it's rigid. In some cases, it's just members. In some cases, it has some flexibility depending on the manufacturer type. Or, for example, rigid platens, it's a Cambridge type device. Or wire reinforced membrane, it's NGI type device. These are the organizations who do the test. And a series of stacked rings to add some flexibility, SGI type devices. So if you summarize all these lab tests, relative quality of test results, for example, resonant column test, it's good for shear modulus, getting shear modulus. It's good also for Young's modulus, and material damping also it's good. But this one is at a lower strain, very low deformation. Cyclic traxial test, it doesn't provide shear modulus directly, but we have an indirect approach, but it provides good results for Young's modulus and material damping. And cyclic simple shear is good for shear modulus and material damping, but it doesn't provide directly the Young's modulus. So we can combine resonant column at low strain and these two at larger strain, depending on what parameter we are looking for. So this is just a general takeaway, what you can get. So another mini project for some of you, one of you or two of you, if you're interested, you can bring short presentation, preferably with some visualizations, some videos and pictures on this, I think, the track gel and simple shear test, the cyclic simple test. So you can choose whichever you like. So this chapter 5, is mainly about getting the data. It's either a lab test or field test. So if you can get the input, and even if we don't have the facility, the equipment at BIT to do these tests, still we can take advantage of technology or Google, YouTube. There are so many universities who did this tests, so you can get that, learn from it, bring it to the class, and teach the rest of us. So we'll talk on this project later, who is doing what. So range and application of dynamic soil tests. So very small strain, 1 raised minus 4 and below, or a small strain you can get between 0.001 and 0.1, and large strains. In terms of the testers, seismic wave propagations, they don't disturb the soil. So they are very low strains. The wave propagation techniques we looked at, they are low strain values. So all this blue line you see, it's the degradation curve for Gmax. G is a shear modulus we get at any strain using any test, applicable test at that strain. And it's dimensionless, divided by the maximum value. That's why it's called Gmax or Gg naught, the original G value, or the static G value is the maximum value. As you are cyclically loading the soil, it's getting softer and softer, weaker and weaker. So the shear modulus is reducing with the strain. So as the strain increases, the stiffness in the soil, what happens? What happens? It decreases. As you cyclically load the soil, it gets softer and softer, weaker and weaker. That's why you see this graph. It's dropping. The G value is dropping. And for damping, it's the reverse. The weaker the soil, as you increase the strain, what happens? The softer the soil or the weaker the soil, is it larger damping or small damping? Larger damping. Very soft soil has very large damping. Clay has larger damping than rock. So the softer, because it does a lot of deformation in it, when the wave passes through it, it damps out. If it's a rigid material, the wave passes very quickly, almost pretty much insignificant damping. So the two curves, always keep it in mind. The stiffness increases, so shear modulus increases with the strain, but damping increases with the strain. The weaker the soil, the more damping it has. So seismic wave methods, they are very low strain, less than 0.001. And resonant column test is also very low strain, approximately from 0.01. You can go up to 0.1 and lower. Cyclic track gel and direct shear tests, they are small strains within this range, 0.001 to approximately 1. And large strain is the soil is being deformed significantly, like a slope stability problem. When the slope slides, it's a significant damage. Or when you are damaging and disturbing the soil in situ condition, doing CPT, SCPT tests, compenetration, standard penetration tests. And we can still get the Gmax and the damping values, but using correlations. Conventional soil types like CPT, SCPT tests, they provide large strain values. So large strain, if somebody asks you what's the large strain problem, slope stability is a large strain problem. The slope slides. We allow the slope to slide and to fully mobilize lateral stresses. In case of designs, machine foundation is a small strain problem. We don't design machine foundations to have significant strain. It's a small strain. Retaining walls is one of largest strain. Foundations, you can allow it to have settlement. You are allowed some value of settlement. Or tunnel designs, or slope stability. Those are large. This is like in a failure case. If a strain reaches one and beyond that, it's like a failure. So this is just general, what the tests are, what strain value they provide. For example, you're not allowed to use a shear modulus which is obtained from CPT, SCPT test for a machine foundation design. Machine foundation design, it requires a small strain. Those values, they should come from either seismic wave methods or resonant column test, or in some cases from cyclic traction and direct shear testers. So depending on where you are in the chart, you can see what is applicable, what is strain level. Other large strain lab tests for large models. One is shock table test. Shock table test is you have significantly large shock table, let's say in this case 8 foot, which is about 3 meter or 2.5 meter by 6 foot, approximately about 2 meter, and a depth of 4 foot. It's more than 1 meter. That size, you can fill this box with soil. And then you can apply seismic input motion laterally using some actuator coupling. And if you check it now, you're using a shock table test. So this requires a big facility, a big lab. In some cases, the shock tables, they are full size. You can find 10 meter by 10 meter by 10 meter height. It's huge. It's probably the size of even maybe this room or a little less. So it's a large scale test, but can be performed at a small scale to full scale. Can reduce the scale or it can be full scale. It provides valuable insight into liquefaction, foundation response, dynamic earth pressure properties, etc. So if you are studying the dynamic earth pressure, you can put some monitoring equipment, accelerometers, pressure meters along the depth and measure how it varies during the shaking. Or you can put actual foundation on top and see how the settlement and how bearing capacity failures, everything occur during seismic. So this is just one example, shock table testing for liquefaction study at Penn State. Penn State is Pennsylvania, as in US, it's one state in Pennsylvania. They did this research for liquefaction. We didn't look at liquefaction yet, but liquefaction is when the soil liquefies, it pretty much becomes liquid and it loses bearing capacity. You'll have significant settlement. I showed you in the chapter 1 in the introduction section where, significant liquefaction happening because of the Niigata earthquake in Japan. Cars and buildings getting, swallowed in underground. So those tests, they can be done in a small scale or large scale tests. You can follow this link in YouTube and watch the video. Let's see if it should be there. Thanks for those generous researchers who put it for free for us, but you can learn from it. Should be available. It doesn't have sound, unfortunately, but you can see some actions and the shaking and things like that. So you see all this instrumentation, this wiring, some transducers, accelerometers, pressure meters at every depth, and some shaking being applied on it. And they are continuously monitoring the output along the depths. So it was initially completely saturated. Now you see some water coming up, which is being liquefied. So you can go and see, these are high-level researchers, PhDs, in some, maybe in some cases masters researches, which are done to understand the behavior of soil during liquefaction. This is only soil in this case, but you can have foundations. You can have foundations implemented, or, piles, and see what bending moment and shear forces acting on the pile from a liquefied soil. So there is a lot of research being done, and it's already, some cases, some already done. That's why we are able to see or find this freely available lab tests for check table. So sizes can vary for check table depending on the goal. For example, in this case, this laminar box, you can see it 9.5 meter by 5.5 meter by 2.16 meter. It can vary significantly. And the goal is to monitor, continuously during the checking. You have seen those wires and instrumentation inside the soil. And then the next is data processing and try to understand what happened during the checking. The other lab test is centrifuge test. I don't think there is one in Ethiopia. Check table there may be, I'm not sure. It's not that complicated, maybe affordable. But centrifuge test, it's too expensive. It's too expensive. The idea is the equipment generally looks like this. And what it does is you can have a small model, very small model. And if you spin it, so this spins during the test. If you spin it at high G, when we are sitting on the surface of the ground, only 1 G is acting on our body, right? But you can spin objects and apply large centrifugal force on them, right? The more the spinning, the larger the centrifugal force, radial force. By doing that, actually what we are doing is we are increasing the gravity acting on that object. So this check table, for example, you can fill it with soil. Let's say you have a sand in this box and put it in the spinning centrifuge and spin it at high G. So if we are simulating a situation where with a high G, all you can do is just spin it. If you spin it, there will be high G applied. Depending on the spinning, let's say it's Ng. You have 1 G normally, but if you can apply Ng 10 times, 20 times. This concept is applicable for different researches. NASA uses it to increase the gravity on astronauts or things like that. It's not only like geotechnical engineering or seismic simulation. It can be done in other applications, but you can simulate a high G condition on Earth by spinning objects, by applying large centrifugal force. So what it does is, if you apply high G, now what it does is we can simulate a small scale centrifuge model to represent a large prototype. This may be a dam model. Let's say you have a dam model within this box, but let's say it's 1 meter by 1 meter size in the centrifuge test. Depending on how much you spin it, let's say if you spin it 20 times G. So this is a conversion factor for length. If the model is N times G, then the prototype can be 1 over N. So if you have like a 1 meter model and N is 20, then actually you're representing 20 times of the model. So a dam 20 meter high, you can model it actually with 1 meter in the centrifuge. So N is like a conversion factor. All this length, mass, time, velocity, that's with respect to N, where velocity remains constant, it's 1 times. But acceleration is N times. Because acceleration is, if you apply N times force on the dam, then that's equivalent to N times model. So a 1 meter size in the centrifuge can represent N times size in the actual realistic model or prototype. So this centrifuge is very expensive equipment. The idea is clear. It spins and creates a situation of high force. So this in US, there are about maybe 8 universities or 5 universities which have this simulation. And it's a very common geotechnical equipment for testing large sites, dams, and very complicated liquefaction situation. Because in check table is 1 to 1. Check table, if you see it here, we are not spinning it, right? We're just checking it. So it's a direct relation 1 to 1. But centrifuge's advantage, a small model can represent n times of the actual prototype, which means a 1 meter model, if we spin it, if we apply, let's say 10G, so it's the size of 10-meter dam. So that's the beauty of centrifuge test. Physical model with a small scale and high G spinning helps to get simulation for large model. Complex soil structure interaction, small scale buildings, rocking foundation, etc. can be tested. This one, let me see. This is NCU, Northern Central University, San Diego, California. And this one, it's RPI. This is where RPI is the school where I did my PhD. They have one centrifuge there. I didn't get a chance to work with it because only PhDs with a lab test, they work on it. But I have seen it. I go down and it's under the basement and I help them and see the equipment. So when it spins, everything is locked. Nothing is around. Because if something breaks, it's catastrophic. So the idea is what it does is, you see it, this is our PI model and platform during test 1. Where is it? 1. So what it does is you have this model. So the model gets in here. Once you have your calibration and everything, the sample put it here. And when it spins, this gets into this position. It's loose. It's like a hinge joint. If you spin it a high G, it gets like a horizontal. It moves this way. So whatever you see here during the shaking, during the spinning, it's like this. So the RPI, it's able to apply earthquake shaking at the same time, while it spin it to create a high G condition, right? But the spinning doesn't apply dynamic load. So to apply the dynamic load, there is a shaking we apply at the same time. You spin it, at the same time, apply the cyclic loading. So we are simulating earthquake condition. So there are 2 things. Spinning by itself, because it's a dynamic, it's a rotation, it's not a dynamic test. All it does is it creates a high centrifuge force and it introduces that high G. But together with that spinning, you can apply earthquake shaking in any direction. In this case, there is a horizontal shaking applied. And this one is centrifuge at University of California, Davis. It's 9-meter radius. This is probably the largest. All of them, they have the same principle of working. You put your sample here, depending on whatever research you do. There are so many PhD researches being done here to understand behavior of soil at different conditions, or with dams and foundations, so many conditions. But you create your model, then you spin it. So this is one thing. I'm just introducing you about these testers, but whoever is interested, again, there is a chance for mini project here too. Go to the internet, get some centrifuge test, understand it, and bring something new for us, and let's learn together. But these tests are worldwide. They are there. India, I'm not sure if India has, but China has one, not one, probably more. Europe, they may have more. In US, at least 5, they should be there. So there is a weight of 10% for this mini project. Just take it seriously, try to understand it, and you'll go deeper if you get opportunity in the future. Right now, it's just giving you, okay, something like this is already there. So if you may get PhD opportunities, research opportunities to work on these equipments. So like I said yesterday, Don't feel bad not having these equipments in Ethiopia. Even I went outside, I have seen it, but I haven't done it. I haven't done anything with it because my research was more of numerical and coding like that. But my research was simulating whatever they are getting from centrifuge tests, but replicating that in softwares. That's what I did. So somebody did a centrifuge test, then I replicate that in computers. So my task, it's somehow related, but I didn't get a chance even to play or to do anything with this. But I had a chance, to see colleagues how they prepare the models, how they run, how many simulations they do. So don't feel bad at all, not having it in Ethiopia, or in the future you may get a chance to work with it. But just be familiar. So stress, strain behavior of cyclically loaded soils, whatever test we do, our final goal is to get some dynamic properties of soil. Can be cyclic shear, cyclic traction, and then if you do repeated test, and we get those high hysteresis loops. If you connect the endpoints of the hysteresis loop, you will get something called the backbone curve. So a typical soil subject to symmetrical cyclic loading can exhibit a hysteresis loop as shown in figure below. When you perform shear testing, the actual shear modulus changes with the strain. So you see these hysteresis loops, they are getting flatter and flatter. So if you have a plot of shear stress and shear strain, what do you get? What's the slope? Is that elastic modulus or shear modulus? Shear modulus. Shear stress, shear strain, shear modulus is the slope. Now, look at it. When you start the test, if I make a tangent to the first data, pretty much this is the line. So the slope is much higher, right? If I go somewhere in the middle, let's say maybe here, now the slope is getting flatter. So here G, I have one G, another G, several G values. See this backbone curve, that's getting you the second modulus or connecting all the dots, the tip pointers. So is that getting flatter and flatter? When the slope gets flatter, what does that mean? G is increasing or decreasing? G is high initially, pretty much at a static condition. The more cyclic loading you applied, the G is decreasing and the slope is becoming flatter and flatter. So there are different G values that we are interested in geotechnical engineering. If you consider one hysteresis loop, the initial one, we call it Gmax, or the maximum shear modulus. That's the initial one. If you remember in the degradation curve, what I said, you have a degradation curve where the G is decreasing with cyclic loading or with a strain, and we normalize it with Gmax. And the maximum it can be, that curve is 1, GG max. Right? That max G value is the initial value here, this G max you see. That's the maximum it can be. The other G's are during the cyclic. It's getting lower and lower, smaller and smaller. So that's why, because G is getting smaller and smaller with the strain, your curve is getting degraded or lower and lower. So maximum shear modulus, Gmax is the initial one, is initial stiffness of soil at a small strain, and is usually used for linear analysis as soil behaves linearly at small strains. That's at the very smallest strain. We don't have significant damage in the soil. So we can use it for linear analysis. Like whatever force you applied, it's acting linear. Tangent shear modulus. Any point within the hysteresis loop, you can make a tangent. Any point you're interested in. For example, this point. So that's called the tangent. It's tangent to that hysteresis loop at any specific strain. Is stiffness of the soil at any point during loading process, and is usually used for nonlinear analysis of geotechnical problems. You probably have heard of those cognitive models developed for nonlinear analysis, or you'll see it in Plaxis and FLAC. There are some cognitive models developed by researchers. All they do is that they're trying to capture this G-tan at any strain. They're trying to provide the value of the shear modulus at any strain, which is along this line of the hysteresis loop. Different soils, they have different cognitive models. And because you are getting it at every point, it's good for nonlinear analysis of geotechnical problems. The G is changing at any point, at every point of the strain. But that's also difficult. If you try to do that, it has its own disadvantage. It's advantageous because you can get a full nonlinear analysis, but it's time consuming and may not be easy even to get those cognitive models correctly. But that's the tangent shear modulus. So usually what's being done is we take average for a hysteresis loop. That's the G second. If you connect the 2 endpoints of the hysteresis loop, it's representing an average value for that cycle of loading. So second shear modulus is the average stiffness of the entire loop, which is usually used for equivalent linear analysis. Equivalent linear analysis, it's not a linear analysis, but it's like we are like a pseudo-static analysis. It's non-linear, but we are using an average value. Piece by piece, we are doing it at every point, and it's like to represent the linear condition, but with average values. So it's more practical, doable, less time consuming, and less expensive. So those softwares like Shake and Sassy, that's what they do. That's how they model soil for dynamic analysis using the G second. And Plaxis and the FLAC, they have cognitive models using G-tan at every point within the curve. So when you get a chance, we'll talk at the end of the course. When you do Plaxis and the FLAC, you will see cognitive models by different researchers trying to come up with the best nonlinear analysis. But it's not that practical. It's good for research, but for design purpose, nowadays we are using this equivalent linear analysis using an average value of G. And softwares like Shake, which is a wave propagation. I gave you one mini project on it. Did I? No, not yet. It's in chapter 9, I'm sorry. But you'll have a chance to play with Shake. There is edu Shake version. You'll apply some seismic input, and there are free softwares for students. So you'll do that. And Shake and Sassy. Sassy is one of the best softwares to model soil structure interaction analysis. It models both the soil and the structure. In the soil, they have wave propagation technique, and the structure, it has like finite element method, like StatPro and SAP 2000. So it can model everything together in one shot. Because structural engineers, what they do is they approximate the soil. They either assume fixed condition or they apply some springs when they model it. And geotechnical engineers, they assume some approximation on the structure because we are more interested in the geotechnical portion. We do a detailed modeling for geotechnical part, but for the structure, we approximate just some mass. But when you come to softwares like Sassy, it models everything as is. And it's much faster than any available software. Usually it's too expensive software. We use it on nuclear power plants and high-level dams, very expensive critical structures. You don't see it being used in commercial applications, like for design of residential buildings or things like that. But for critical structures such as nuclear power plants, that's what we use for seismic analysis. We are forced in US, the Nuclear Regulatory Commission in US, it forces us to use this kind of softwares for analysis. Because accuracy is very important, because it's a high-risk investment. There are accidents, potential accidents to come, so they need more realistic simulations. So Sassy is what I use mostly. for design of nuclear power plant, especially for seismic analysis. It doesn't mean that we don't use Plaxis and FLAC, we use, but only for the geotechnical part. But when you combine the two, it's SASE. We'll see a little bit how it works both Shake and SASE. Chapter 9, I have an introduction part on it. We'll look at it. So equivalent linear properties for hysteresis loop. We already said if you connect the G-second, that's what we use mostly. The Gmax is the initial value. In the shear stress, shear strain graph, that's what it means is the G-second is the backbone curve is what you have from several tests. And the damping ratio, we have seen this in chapter 3. You can calculate from any test. If you know the dissipated energy and maximum strain energy, the damping within the soil can be calculated. You can calculate it either this way, or you can use resonance column test results, power bandwidth methods, or logarithmic decrement methods to get the damping ratio. So shear modulus degradation curve, I mentioned it previously. So you have a loop, you have a backbone curve. So at every point you have shear stress and shear strain. You can really convert this backbone curve into a Gmax curve, right? Once you get the backbone curve, at any point you have shear stress and shear strain, and you know the maximum value, which is a tangent at the original condition initial state, the lowest strain state. Then converting into a backbone curve to a Gmax curve is pretty straightforward. This is what the lab technician will provide you. If you're the guy interested in doing like finite element simulation, finite difference simulation, this is your input, Gmax curve. You want to know the value of G at every strain. For static analysis, you don't do this. But dynamic analysis, you need it. For every input, you want to pick the value of G and get the stresses. So this Gmax curve, this is just dimensionless. You can call it also a G curve or degradation curve. If you divide it by the initial, the maximum value, now it's dimensionless. There are companies, organizations providing this curve for general properties of soil, but in conventional designs for critical structures, you have to do a lab test. Do whatever wave propagation test, borehole test for the site, get samples, do a lab test, and develop this curve. Once you have this curve, now you're ready for a computer simulation. So we're getting close to how you model soil for dynamic analysis. Modulus reduction curve, as the name implies, because it's reduced with the strain, is an input for equivalent linear analysis of simulation. It provides stiffness of soil at different strains. Estimating Gmax. It may not be easy sometimes in the lab getting Gmax. If we get it, that's good. But if we don't get it, you can get VS of a soil from lab test, and the max is the density of the soil times VS squared. Modulus reduction curve can be developed for various types of soils. Reduction curve. The best way to obtain Gmax is through low strain field tests. Those wave propagation tests we discussed yesterday. Yo, are we doing good with our recording? Yes? Okay. So maybe that's the problem yesterday. Somebody has to log in. The best way to obtain Gmax is through low strain field or laboratory tests. Since most seismic geophysicals induce shear strain lower than 1 raised minus 3, the measured shear velocity can be used to compute Gmax. If you remember yesterday, for any layers, 2 layers reflection, refraction test, we can get the VS, right? Apply your source at some point, record it at other point. From the direct wave, at least for the first layer, we can get the VS at low strain. If you get that VS, This is a low strain value that can help you to estimate the Gmax. If you don't have Gmax from a lab test or field test, there are correlations you can use. If low strain tests are not an option, we can also rely on various correlations to estimate Gmax. Not as good, but better than pulling a number out of thin air. So there are generic equations from lab testers trying to estimate the Gmax value. Different researchers provided different equations for different kind of soils and environmental conditions. So in this case, F is a function of void ratio, generic equation for a lab test, OCR over consolidation ratio, blah, blah, blah. Can go the list. So, but you can do different researcher equations to estimate it. If you don't have anything, you can still use some available correlations. This is not the only correlation. You can have for sands. You could use a SEED and IDRIS 97 empirical correlation. Or there are several other equations. Refer to table 6.6 in reference 1, the Kramer book. For many other numeric empirical relations developed for various field tests. You can go through it. Or whenever you need it, if you are doing some kind of research, you can come back and look at this. Right now, you don't need to memorize any equation or things like that. I'm just introducing you, these things are available. If you are lucky and have a lab data, that's good, you can use that. Or a field data, field test, you can use that. If nothing is available, just look at research work. There are different correlations, and you can pick one which closely matches with your purpose. While there are many factors that affect the modulus reduction behavior of soil, the two most significant factors are soil plasticity and effective stress. As the plastic index increases, what happened to the Gmax curve? Plastic index 0, 15, 30, 50, 100. Gmax increases or decreases. Let's pick some strain value at 0.1, let's say. Mahadar Salam, this is a question for you. A soil which has 15 plastic index, which is this, at 0.1 strain, compared to a soil with plastic index of 100. Which one has large G value? Yes, it's the 100, correct. Because G is this value. The larger value is the one with the 100. So this is telling us the higher PI for soil, the higher Gmax. How about with effective stress? At some strain 10 raised minus 3, if you have larger effective stress, let's say this curve has 1 kilonewton per meter square, the G value is here, and another one 200 kilonewton meter square, the G value is here. So as effective stress increases, G value decrease or increase? Increase, good job. So that's just, a pattern. That's general observations. You can go through it. There are so many other factors affecting Gmax. You can increase all these factors and see what happens to Gmax. You can look at this reference 1, figure 6.44, effect of cyclic degradation on shear modulus after Vosetic and Dobry. Dobry is he's the one who taught me soil dynamics in US. He's very famous. He's considered like one father of soil dynamics. He's retired by now, but he has so many publications, and you'll find his name in Kramer book and so many places. He has his own book also, I think after I left RPI. He's a professor in RPI. And this Vosetic is, I believe, his PhD student in the old days. So they develop so many relations. They do a lot of lab tests. Damping curve is similar to what we discussed for Gmax curve, but now see what it looks for damping. Damping ratio increases as strain. Helen? If a strain increases, damping, what happens? Increases or decreases? Increases. So it increases. It's the reverse. The weaker the soil, the larger damping it has. You can get this. This is the final product of a lab test. You can get this from a lab test. They develop it the same way that we developed the Gmax, but they computed damping at every strain, then they plot it. So we don't call this degradation. It's a degradation curve. Even if it is increases, when we say degradation, which means when the soil degrades, when the soil gets weaker and weaker before it fails. So if somebody mentioned to you degradation curve, it can be both Gmax, G curve, and damping curve. When the soil degrades, damping increases. So these are direct output from a lab test and an input to what? Where do we use this? We will check. Where? Where do we use the Gmax and damping curves? Why we are spending so much time discussing about it? Anybody? Yes, we get them, but what do we do with it? We do lab tests, we do field tests, then what happens? What's the purpose? Fakadu. Yes. They are input to a dynamic analysis. We are getting ready to do a finite element simulation. This is an input to a finite element analysis. When you do your shake or ProShake or SASI, any analysis, this is a direct input to the software. So you go out, somebody go out in the field, do a field test or a lab test, prepare the data and the input. This is the input. Then the geotechnical engineering, maybe the same person or a different person, this is an input to a software analysis. So when you think of dynamic analysis, either in Plaxis, FLAC, Shake, SASI, or whatever software, these are direct input. This is the damping value of the soil at every strain. This is the equivalent linear properties. So similarly, variation of damping ratio of fine-grained soil with cyclic shear strain amplitude and plasticity index. Different plasticity index affecting damping. The higher the plasticity index, is that the lower or the higher damping? The higher the plasticity index, let's say 100 at 0.1 strain. What happened to damping? High plasticity index soil has less damping than low plasticity index. You see it? The curve is getting lower and lower. One soil type has only one curve. The purpose we are doing multiple curves is because you can have various types of soils. Similar to the Gmax impact by different parameters, you have also some factors affecting damping ratio. For example, as the void ratio increases, the damping decreases. So this is a general observation. As the confining pressure increases, what happens to the damping? Decreases. When you have larger confining stress, what does that mean? Is the soil getting stiffer or weaker? When you confine it, it's becoming stiffer, right? If something is stiff, damping is lower. A loose material has larger damping. So just go through it to understand what parameters affect damping. So damping Gmax curves are mostly developed together. So from a lab test, you get both together like this. This is what you get as input. Gmax curve for different conditions, different soil. It can be even the same soil but different depths. At different depths, they will give you some curves. But because when depth varies, what varies? At different depths, your effective stress is different, right? As you go down, effective stress, what happens? It increases. And as effective stress increases, it affects Gmax curve, right? So this is a sample how you get it from lab. For different stratification, different depth, they can give you different values. Same with damping. It's varying with effective stress. That would be the conclusion of chapter 5. And it's very practical, very interesting in soil dynamics because it touches both numerical simulations and field tests and lab tests. The purpose of this chapter is getting the dynamic properties of soil, the shear wave velocity, P wave velocities, and finally the degradation curves, Gmax and damping curves. The Gmax damping curves will come to it where we use it, especially in chapter 9. Would be very interesting how you use it. So the main reference for this chapter is reference 1, SL Kramer, chapter 6, and reference 2, Braja M. Das, chapter 4. And you have a homework problem. Review example problems 4.1 to 4.8 on reference to chapter 4 and submit as homework deliverables. I just want to, it's already solved, I believe, but I want you to look at it, write it, understand it, how it is done, and submit it as deliverable. Some topics in the example may not have been covered in class and are expected to be what? They are self-study. If you see something new there, just go through it and look at it. So every homework I assign, it's due 2 weeks after the completion of the chapter. So I expect you to submit these homeworks 2 weeks from now. Is that okay? How is the recording? Where is it? Okay. Thanks.